I've got 3 more classes to do 11. It's a big chapter, different to what we've done, so let's take our time. I won't get through all of 11 for the test. The test is a week today. Exam 3 is heavily mechanistic, it's heavily stereochemical, it's heavily regiochemistry, stuff like that, from chapters, wherever we went to, 8, 9, 10, 11, wherever we got through. Practice old material, practice the exams, come and ask some questions. Tyler has a practice exam for you next week. Do what you can to do well on this exam because there are a lot of points left, and most of the people who are left here are passing. If you're not, there are plenty of points to do so, but you need to get them. Now, I'm in chapter 11, I'm talking about the possibilities of what can happen when we make radicals. Radicals now are a new type of system that you haven't seen before, in which we have the single electron. We have 7 electrons in carbon instead of 6, and so that carbon is reactive, but in a different way to the way it was when it was a carbocation. And we're going to generate these things today. We're going to see a different type of mechanism that we have to write in a different order to be able to make it make sense. And we start off with just defining what can happen. Right? So we've got to keep in mind that you have a flask of molecules, you're building towards biology or chemical engineering where the systems get bigger and bigger, and we're trying to define the very simple molecular things that can happen when you produce a radical. So the first thing we'll see today as we start into the free radical halogenation of methane, that's a big, big mechanism that leads into the rest of this chapter, is that you must initiate or start the process. You must heat things up, you must shine some light on something to put enough energy in to make some molecules break apart to make radicals. So we'll see today that if we have something like a halogen, Br, this is pretty easy to do. Those are inherently weak bonds, and they want to break apart, just like the OO bonds did. And what we'll do here is put in some light or some heat. Delta is the heat, and H nu is the light, and you'll basically make this molecule break apart. It's stable as it is at room temperature, but you start to put some energy in, you can make this thing break up, and you can produce radicals. You'll find now that radicals are reactive. Radicals want to go after something else to find something to react with to give them back their stability. So when we see double bonds, we've already said that double bonds have a pair of electrons that offer, very much like a lone pair. A double bond can give an electron or 2 electrons to something else. So this X dot here, the radical, sees a pi bond, and where we saw with electrophilic addition double-headed arrows, now we're dealing with single-headed arrows. And that's the first big decision you make next week when you see this exam. Is it radicals or is it carbocations, right? And then you make a note of it on the test because you don't want to be daydreaming and end up doing a radical mechanism when it should have been a carbocation mechanism. That's fatal. Don't do that. But in this system, we've got to be careful now because we have more arrows than we saw before. We now have to worry about the fact that there are 3 electrons involved in that process. We have 1 electron from the radical, which only needs 1 electron to partner up with to give a good bond and to stabilize it. But that leaves an extra electron in the pi bond that has to go someplace, and it will go typically to a carbon. And so that step here is consuming a radical on this side and it's generating a radical on that side, and we will call it a propagation step when we get to the summary in a second. So these are events that can happen. The mechanisms that you'll see for the rest of 11 involve these steps. So very much like the processes we saw with the double-headed arrows, proton transfer, nucleophilic attack, leaving group breaking off, these are the same sort of idea catalogued so that you can understand them. We'll also see this is a very important process here, an abstraction of a hydrogen from a molecule. Just behave, will you? X radical goes after some neutral species, some stable species like an alkane, and it strips off a hydrogen, it abstracts a hydrogen. And what that gives you is a stable molecule as far as X is concerned, but it's now transferred its instability to whatever R happens to be. And R maybe will be a more stable system. But then that R radical itself is unstable, so it has to go after something else. And we find now that this is very much like, it's like pinball. These molecules are bouncing around in this system, trying to hit something that they can react with, and if the outcome is good, they will do that process. We'll have to sort of stretch our imagination a second when we start adding all these things up, but these are the things that can happen. We can now take advantage of the fact that this thing is going to be reactive, and it goes after an X2 molecule. Where did X2 molecule come from? It's in there. It's bromine, it's chlorine, something like that. There are more molecules in there to be had. And so what happens here is that the R radical goes after X neutral, and it grabs hold of one of the X atoms to form a stable molecule, but it then transfers the radical instability someplace else. In this case, it goes back to one of the X radicals. You'll see this in context in a minute. It'll all hopefully make some sense. Somebody will ask this question at some point about the difference between adding bromine in the presence of light and heat or the presence of adding bromine to an alkene, as we just did in chapter 9. And we've got to be careful here because some of these processes will be reversible. Go ahead. No, be careful here. I'm glad you said it because that's Friday, right? It's not quite Halloween, but it's close to it. No negatives and no positives. Write that down. Haldeman, take your pencil, that thing that you have in your hand, your writing implement, and write that down in English. In this chapter, there are no positives, there are no negatives, it's all neutral. Radicals are neutral. And that might be a good point, Michaela, because that might be a big problem that people have, is they get mixed up in these things. You cannot do that. You cannot do that. Keep them separate. Radicals are neutral. This process, you don't see an awful lot, but it can happen. The addition of that X radical to an alkene is reversible. It can go backwards, and it can regenerate the alkene, and it can give you the X radical back. That will become important when we have to consider the use of bromine, for example. We've seen bromine add to alkenes. All of a sudden, it might do something different in the radical world. Down at the bottom, something that's a bit of a pain. The engineers will appreciate this when we get there. You find two radicals that bounce into each other in this flask. One has a spare electron, the other has a spare electron. They look at each other and go, right? Bond, because each can then become stable. And that will then be called a coupling step. It will be kind of detrimental to some of our processes, but you end up with losing radicals. And if we've taken our time to make radicals, often taking radicals out of the system is detrimental. We don't want that. Ready, Santigantas? Are you with us today? No, you're discussing your coffee cup, aren't you? I'm very proud of you. Okay. In this example now, we're talking about things that can happen. We have not put them together into mechanisms yet. That's about to happen. But this slide is something that you should be looking at over the weekend, trying to decide what's going to happen, and now we'll talk about when things happen. So here we go on the left, a discussion of what we call initiation. To get these reactions going, you have to initiate them by heating them or by shining light on them, and that breaks apart the molecules to give you the initial radicals. After that, you've got to imagine now. I can't think of a very good analogy of this, but it's like, kids sort of, when you go shopping and you put the kids in those places in Giant Eagle where they have their little den with all the balls in there, right? And you can jump around and they're like, bleh, right? And the balls go flying all over the place. I don't have any kids, so this is sort of my best effort. Chemistry is like that. It's a whole bunch of spheres in solvent. There's a whole bunch of things bouncing around, hitting each other. And if you hit something, you can get a chemical reaction. And why are reactions sometimes slow? Because you have to find the right thing to hit. So when we talk about rates of reaction, it's about finding what you need to hit, and that can take time. Well, in this system, which is about to get very complicated, we can try and simplify it and deconvolute it by thinking of it like that. In a system with one drop of something, you have an unbelievable number of molecules. So if you think about the Avogadro number, 6 times 10 to the 23, that's a mind-blowing number. That's incredibly big. So even in 1 mole of something, you have a huge, indescribable number of molecules. And it's key to go back to the earlier chapters when we said not all of those molecules react at the same time, because they don't all have the same energy at the same time. So why do you spend an hour standing in lab, or sitting in lab, waiting for things to finish through reflux? Because all your molecules need to get over those barriers. They don't all have the same energy at the beginning, and you need to heat them up continually to get them all over that barrier. It takes time. Well, when we see these processes for radicals, it's a similar type of concept. But we're about to use radicals, we're about to use systems in which I seem to consume my radical over here, and all of a sudden I have another radical over here. Where does that come from? And you've got to get out of this sort of very linear process, this very linear approach to chemistry, where you have 1 molecule of this and you have 1 molecule of that. You don't. You have a bazillion of this and a bazillion of this. And they don't all interact at the same time. So we're going to see now that if 1 radical is consumed, you still have a huge number of radicals, and they can get involved as well. So we're going to broaden our sort of ideas here to try and explain that, and you'll see where it comes in a second. Keep an eye on now. Initiation, get the thing started. We're going to talk about chain mechanisms in which something happens to then allow something else to happen, and at the end of this event, we get back what we need at the beginning, and we can go back and do a cycle, a cyclic type mechanism. We're going to call those propagation steps, and then the bad one. Okay? This is not particularly friendly. We don't like this one, because this consumes our radicals. Termination is going to happen. If you have radicals bouncing around a flask, and they see each other, they will react. They won't ignore each other. And if this reaction needs radicals, and you start consuming them, that's detrimental to the process. So now, let's start talking about free radical halogenation. Those are the definitions. We now have to put it into practice, and I have a lot of stuff now between here and next Wednesday for the next exam. This type of reaction, this type of process, where we take something like methane, CH4, and we treat it with chlorine. And we heat this thing up, or we shine light on it to put energy in. And that's going to give us a very, very useful material called methyl chloride. We can think about this now having a leaving group attached. We could do SN2 chemistry with it. It's a nice entry from what we get from the ground, okay, methane, CH4, and we're getting into now organic materials that we can use to do synthesis. We can use to do pharmaceutical chemistry, for example. This now is a very different mechanism from what you've seen. It is going to involve systems that don't have charges, don't have delta plus, don't have delta negative in terms of their reactivity. The overall process seems very simple, and it isn't at all. It is very, very tricky. So somehow I'm replacing one of those hydrogens with a chlorine. I think that's a substitution. So we'll call this a free radical halogen substitution, where we swap one of the H's for one of the halogens. How it happens now is complex. This is now going to involve a series of steps very unlike what you've seen. There are no delta pluses, delta minuses here. There are no nucleophilic attacks. There are no leaving groups breaking off. We're going to see this, and we're going to do it again in steps like this. We're going to hopefully put it together to see it makes sense. I take my time with this. It turns out now, if you have a flask, a reaction flask, a chemical plant in which you're trying to do this, a huge, massive vessel, in which you've inserted some methane gas and you put some chlorine gas in there, and you start heating things up, you have to think logically about what can happen and when things can happen. So if we're heating things up, I would argue that it's logical that the weakest bond should break first. You're putting energy into a system, the weak stuff breaks first. Well, in this example, I think the chlorine molecule is the weakest of those, or the weaker of those two molecules. You have CH bonds versus CL-Cl bonds. CL-Cl are like OO bonds, they want to break, and so we can do that quite easily. And so what we do in the first step, which we call initiation, is some of those molecules get broken up. Not all of them. You're going to break up a small number of the chlorine molecules into chlorine radicals. That allows what comes to happen, what comes next to happen. So I've now initiated the process. I've got this thing going, so now we can start doing chemistry. Think of it physically. Think of it actually in the flask. You had a bunch of neutral molecules that were stable, all bouncing around. Hey, how you doing? Hey, how you doing? And all of a sudden you heated it up, and you made it angry. Okay, so you've got some chlorine radicals in there now that are aggressive. They want to react with something else to become neutral and stable again. So we've now got to consider the possibilities of what can happen if a chlorine radical hits another molecule. And this is just logic. There's no magic here. There are a limited number of possibilities to what can happen, and if you're on top of this, it's kind of fun. So if I've just broken up a small percentage of those chlorine molecules, I have a small number of chlorine radicals bouncing around in this system, surrounded by methane CH4, which hasn't reacted yet, and other chlorine molecules. So those chlorine radicals can do the following. They can hit a methane molecule. If they hit a methane molecule, the realization then is that if a hydrogen is abstracted, you get HCl. And HCl is a good molecule. Over here, the chlorine now is stable because it's HCl. But you transfer that instability onto the carbon. Now, we think about simple things here. What's the difference between chlorine and carbon? You know, where would you rather put that radical? Which would you rather have missing one electron, a chlorine or a carbon? Think about some of the simple systems we thought about, some of the simple ideas we thought in the past. Which is easier to take an electron away from, a chlorine or a carbon? Carbon, because less electronegative, right? We're going back to the very first sort of few days of class. So this should be a good process in which we get rid of the instability on the chlorine and we transfer it onto a carbon. So, you know, hooray for chlorine. It's happy. But the problem now is that we just upset the carbon. The carbon now has 7 electrons. You've now deposited that radical onto a carbon. You're not done. You've got one of the products of the reaction. There's HCl. It's one of the byproducts. But you now also have this carbon-based radical in this big mixture, in this sort of, you know, system where you have lots of molecules bouncing into each other. That carbon radical needs to find something else to react with. So if we take the carbon radical, it can find, for example, a molecule of chlorine. Where did my molecule of chlorine from? I have a huge number of molecules of chlorine. And I only had to break up a few of them to get this to start, to get this to work. So now I'm going to think about the possibility of this reacting with a chlorine molecule. We know that's a weak bond, so maybe it's easy to break it. And on the right-hand side, that gives me chloromethane. Hooray, because that's one of my products. We're getting places. But we also generate a chlorine radical. Boo. Chlorine radicals are unstable. They want to react. And what I've done here is I've generated the piece down there, which is needed over here. And again, I use this idea of linear. One molecule reacts with one molecule to give a product. No, we've got to be careful now because you have a huge, huge number of molecules in this system, some of which are reactive, some of which are not. And once they interact, things will happen. So I have used a chlorine radical here, generated in the first step, and I've hit a molecule of methane. I've taken off one of those hydrogens so that I make a stable molecule of HCl. But I've transferred the instability onto the carbon. That carbon radical now needs to do something to become stable. What else is left in this mixture? Chlorine molecules, lots of them. weak bonds. So if we go after one of them and we bounce into it, we're going to get abstraction of chlorine, which is one of the steps in the previous few slides, cataloging what can happen here. And you end up with the chloromethane, which is our product, and we end up with chlorine radical. Fair enough? So you get back at the end what you need in the first step. And you've got to be careful here. It's not catalytic. This is not catalytic because the chlorine gets consumed. Yes? As you work your way through this system, the chlorine eventually gets consumed. A catalyst doesn't get consumed, so it's not catalytic. Well, that would be fine and great if all of that just happened. And this is where the engineers, you start thinking, all right, you're building a plant. You're starting to think about running this thing, the economics of this thing. If I want to make myself a larger supply of this and then sell it, I want to think about the size of the plant. I want to think about the efficiency of how the process works. I want to think about how much energy I need. Because if I consume a lot of energy, that's money. Well, in the ideal world, if this was ideal, you would take one molecule of this, break it in two, and that would be enough. You would turn the lights on momentarily, and then you would turn the lights off. Because this then gets consumed in this step, but it gets regenerated in that step. And then it goes back and reacts with another molecule. And so every time you do this process in one iteration, you get back what you need for the next step. That's perfect, right? You just have to initiate this once, and then turn the lights off or turn the heat off, which saves you money, because the oil molecules are just doing this all the time. As soon as you get a molecular product, your byproduct goes back and reacts again. Unfortunately, that doesn't work. This is why we have this second box on the right. This is a list of other things that can happen that are detrimental to that perfect reaction. So on the right-hand side, thinking about the good things that happened on the left, we got our products. Great. But you also have to remember that this is a big system with lots of molecules in it, and whatever bounces into whatever else is going to have to consider what to do. So what happens if a chlorine molecule, a chlorine radical finds a chlorine radical? They will bond because they have what the other one needs. They will bond. So let's think about this. If we've done the engineering thing where we've turned the lights on or the heat on for 5 minutes and then walked away and expect this to give me 100% product, it won't work like that. Because as soon as a chlorine atom finds a chlorine atom, it will recombine and give me this. That's what I started with. That's not much use to me. So that process is called termination. It stops the radical process. It consumes the radicals without generating a new one, and you're kind of stuck. So move on to the next one. And these are just logical. If you can come up with other steps that can happen, let me know, because these are pretty much it. A carbon radical can react with a chlorine radical, and they come together to give methyl chloride. Yes, that's the product. Yes, great, we've made some product. But I don't get a new radical formed. I'm consuming the radicals, mopping them up, taking them out of the reaction, so the reaction's kind of struggling. It's running out of radicals. The last process that can happen down here, what if a methyl radical bounces into a methyl radical? They're going to bond, because one has one electron, the other one has a spare. Coupled together, you get a bond, everything's stable. That gives me a product, ethane, which isn't much use to me. So as these processes on the left are happening, these things on the right are also happening, because if they didn't, you'd be sitting there going, why on earth isn't this happening? Radical meets radical, bond. Radical meets neutral system, abstraction process. Everything should make sense. So what do we do, engineers? How do we make this work? Can I leave the lights on for 5 minutes or the heat on for 5 minutes? Or I have to heat this thing all the way through its reaction? Heat it all the way through. Now, why do we have to do that? Make sure you form radicals. Because if I'm consuming radicals over here to make chlorine molecules, I want to re-break that molecule back to radicals. And the sensible way to do that is to heat it up. So if you're continually heating this reaction or shining light on it, as soon as this forms, it will break and become those radicals again. Fairly simple way to get around it. Now let's think about possibilities and sort of statistics here. If I've broken only a few of these chlorine molecules at the beginning, I don't have many of these chlorine radicals to start with. And so I have a low concentration of those radicals throughout this process. And some of them get consumed on the right-hand side, and some of them are used on the left-hand side to do propagation steps. And I can say now that, yes, I should have chlorine radicals in that mixture all the time if I keep heating it. Because even if a chlorine molecule reforms, it will break up and become chlorine radicals again, and we'll keep going. Well, what about these things down here? What are the chances of this happening? If I've got a very low concentration of chlorine radicals, what are the chances of this type of process happening? Low or high? They are low because there aren't many of them. So they do happen because you have that possibility of finding them, but it's not going to be a major process. You're going to get most of your product from this propagation idea over here, and a very little amount of it from that step over there. Now this step is a dead end. You can see how this sort of tails off. This step is a dead end. You're not breaking that carbon-chlorine bond because it's a strong bond. So these now are going to funnel the radicals out of the process. This reaction also gets rid of some of the radicals, and we end up with this byproduct, which we don't particularly care about. So you get high yields, but you're not going to get 100%. You can't. That's a lot to think about. Have some coffee. Talk to your brother about it. Whatever you want to do. Yeah? Ask some questions. Get your head around it, because it's not easy. Joe? Not quite, not quite. The argument for the engineers was, in reality, if you're trying to do this for a money-making process, it would be nice if you just could turn the heat on for a second, get some radicals started, and then turn the heat off, because heat is money. And that would be great if that then allowed the radicals to go and do their thing and give you a high yield of product. But the problem is the right-hand side of that picture. You get these termination steps in which the radicals get consumed. So you keep the heat on, because as soon as that chlorine molecule reforms, you can break it back open. So you're continually generating chlorine radicals. Make sense? Yeah. So you get very high yields of this process in which a chlorine replaces a hydrogen through a radical reaction. Go ahead. Oh, I don't know about that much. Think about chlorine. In fact, if you do a chlorination, it's usually in reflux. I don't know, reflux in toluene or something like that. 100 degrees at most. It does not require high temperatures. Go ahead. We need to do rates in a minute. We need to talk about chlorination versus bromination. That's when we'll talk about rates, because that makes a big difference in terms of the outcomes. I'm sorry I've spoiled your weekend, but hey. Right. There is a very sensible, very clear way to draw this out, because if you think about this, it's not quite as simple as what we've seen before. What we've seen before is sort of systems in which I go from A to B to C to D to E to F. I end up at the product. Those are the mechanisms you are happy with so far. What we now have is sort of a description in a linear sense to keep a track of everything, because it's getting more complicated. So this is a very simple way to write this out. If you're asked for the steps for this free radical halogenation process, this is the way you do it, regardless really of what the substrate is. The substrate here is methane. Obviously what's going to happen next is more complicated systems. So we're going to say that to get the reaction started, you need to heat things up, you need to break your halogen into two. That gives you the radicals that are necessary for what's to come. That initiates the process that we'll call initiation step. That's the only initiation step possible right there. After that, the chlorine radical is wandering around thinking, I need to find a hydrogen or something to react with so that I can become stable. Now, be careful here with the arrows. I've got one electron from the chlorine, so I use my single-headed arrow. I only need one electron from the CH bond, but I can't take just an electron. That's too much energy. That's an ionization type process. I don't want to do that. I can think about this bouncing in. Think about this transition state for this. Carbon radical is hitting the hydrogen. The carbon-hydrogen bond is breaking. It's just like this coming in and this coming out, but with different arrows. I need to take off this hydrogen because that gives me a neutral molecule of HCl, and I then deposit the third electron onto the carbon. That's where my product comes from here, which is one of my products of the reaction, and I now have produced a new radical. So initiation is fairly obvious. You need to get the reaction started by heating things up to make the radicals. The propagation steps then are a bit more confusing, because as you consume a radical on one side, you produce a radical on the other side. That's a basic definition of propagation. Consume a radical on one side, produce a new radical on the other side. Because that keeps it going. It keeps the chain growing, which is the word propagation, and so that allows the reaction to go. So propagation here, yes, I've got one of my products, but I now have a carbon radical. That carbon radical is bouncing around this system, wondering what to do. If it finds, in this case, a chlorine molecule, away we go. Why is it logical to break a chlorine-chlorine bond? It's weak, right? It's quite weak. It's a weak bond that can break quite easily. So when I think about the arrows for this one, I'm going to take my radical carbon. I'm going to pick off a chlorine in an abstraction step. Is that it, or do I need more? I need one more arrow because I have a third electron in there and it has to go to the chlorine to compensate. People who struggle with this forget that third arrow. Now that gives me on the right hand side chloromethane, great. That's my major product, that's what I'm trying to make. And it also gives me chlorine radical. Propagation step, because that has produced a new radical where we consumed one. But nicely, this can now go back in, find another molecule of methane, and do this again. So people will say, all right, dude, First of all, don't call me dude. They will say, there's a chlorine molecule. You've just used your chlorine molecule. Where on earth did this chlorine molecule come from? Did I just add it? No, there's a huge amount of this stuff in there. And you're consuming little bits as you go, and there's more there to be used. The problem with the reaction, the detrimental steps down here, carbon, carbon, come together, give you termination steps. That's a dead end. You're not going to do much else with that. Down at the bottom, chlorine radical comes together with chlorine radical. Do I need a third arrow here? No, because I've got 2 electrons, 2 arrows, bond, finished. I get my product, which is great, but that's the dead end. I don't get any new radicals. Now you're practicing exams, you're practicing stuff for next week, obviously. This weekend is going to be big. Think about this. The question I often ask is, give all the steps that produce the product. I don't want people memorizing stuff if I can help it. I want them understanding it. So I would ask a question based on, okay, give me the steps that produce the product. So the major step that produces the product is this one, the propagation step. That's where I get most of my product from. But I also get some product from down here, which is a termination step. So chances are you're not going to be given a question that says, just tell me the reaction mechanism, because that's memorizing. I don't like that. It's going to be, what's happening here? Tell me what's happening. Understand it. Understand it to explain it, type of deal. Fair enough? Okay, moving along. Anybody on that slide? We're about to add a lot more detail to this when we go to tertiary, secondary, and primary hydrogens. So the overall process is that you've mixed methane with a chlorine radical, and you've mixed the methyl radical with the chlorine molecule, and you end up with these 2 products. And the book likes to do it like this, where we subtract out the radicals, and we end up with this molecule reacting with chlorine overall to give chloromethane and HCl. Very useful industrial process. And to us as chemists, a very, very powerful reaction, because we can go from molecules that purely have alkane-type structures to activated systems. You can enter a different world now. You can go from the alkanes, which have very little to do in terms of activity. You can put a halogen on there. You can do eliminations. You can do substitutions. Do whatever you want. This is also useful industrially. You can see here what we just did. If you take methane with chlorine and you heat it up and you make methyl chloride, you can go further. Have a lot more chlorine, let it go longer. You can end up with methylene chloride. Where have you seen that before? Lab, it's a solvent, yes, dichloromethane. And then you go to chloroform. What's that used for, or was used for? Kidnapping. Well, why not? Yes, for putting people asleep. And carbon tetrachloride, you're probably too young to remember this, but what's that used for? What was it used for before it started killing the atmosphere? Yeah, aerosol, dry cleaning. Okay? It's very difficult to get hold of carbon tet anymore because it is kind of dangerous, and I have a bottle and I'm not telling you where it is. Okay. We've got to then worry about the consequences of this in where you want to go. Many of you are interested in pharmacy, medicine, biology, stuff like that. And this also is detrimental in polymer chemistry for the engineers. If we produce these radicals, they seem to be very reactive. They seem to just wreak havoc in a system. They go rip things off all over the place. And yes, they do that in your body, and they do that in the atmosphere. So radicals are a real issue in terms of medicine, in terms of technology. So we've got to worry about, first of all, how you make them. And then in the second slide, how you get rid of them. How you scavenge them. So I want to point out these possible inhibitors. You'll mostly see, initiators. You'll mostly see chlorine, you'll mostly see bromine. But we need to be aware of the third one too. Why is it logical to break this bond? Why is it easy to break this bond? It's weak. This one here we saw with peroxides, it's weak. You can see where we're going. We have a reaction that we haven't dealt with yet, HBr with peroxides. This will be the beginning of that in the next couple of days, when we actually explain the outcome there. It's an anti-Markovnikov addition of HBr through a different mechanism. What is that different mechanism? Radicals. So we can also do this with things in the lab like benzoyl peroxides. These are compounds that are advantageous to us because they're usually organic soluble. The organic group right there makes it organic soluble. Dissolves up in your system, away you go. But they're the same idea. That weak bond is in the middle, and it's weak, and it breaks open to give you 2 radicals. So that's a way to get reactions started, is to initiate them with a radical initiator. The problem is, in biology, people are starting to understand now that radicals are an issue. You think, any of you into the health foods and whatever, you talk about foods that have lots of free radical inhibitors and things that will pick up radicals in the body and absorb them. These are the types of things. Oxygen, which we kind of need more than your cell phones, is a diradical, and it can cause all sorts of problems in the body. You think about this radical, it can do all sorts of things. So we have to have compounds that will pick up radicals and mop them up. This is just FYI, but it's just an example of where it's useful in biology. If you produce carbon radicals in your body, you can actually get rid of them with hydroquinones. You can take this thing here, we can go after this hydrogen here, and we can pick this thing off, and we get a resonance stabilized radical at the other end. That's kind of a one-way street, isn't it? That's going to the right-hand side and it's not coming back. So that's a way of mopping up a radical that's detrimental. And we can do that again down at the bottom, where you have a second hydroxyl, do the same sort of process, and you end up with this, which then combines to give you benzoquinone. Okay, so there are some medicines out there that rely on this type of thing, and in your lifetimes I would hope that we know more about radicals in terms of medicine, because they are quite dangerous things. Well, back to the halogenation, the organic part of it. In terms of what's going on here, we need to understand that the process is viable because what you get is more stable. I think this is logical so far. If you're mixing bromine with something, that bromine wants to react. That bromine is a weak bond and it wants to become something else. So the thermodynamics here makes sense for the right-hand side. And if I go back to methane plus CH4 plus an halogen, and I go to the right-hand side, do I get any change in entropy, really? Not really, no. You're going from 2 to 2. So it's all about enthalpy here. It's all about breaking the weak halogen-halogen bond and forming stronger bonds on the right-hand side. You can get those numbers quite easily, and then you can say for sure that that's going to work. So over here, it is the loss. What is the motivation? You'll see that on my exams. What is the motivation or the driving force for this reaction to work? And the answer is the breaking of that bond. You want to get rid of that because what's on the right-hand side is more stable, so therefore it's a good overall exothermic process. Everybody okay? Where is everybody? Oh, I'm sorry, it's Friday. I should know by now, shouldn't I? There's a huge gap up there on the top. What a lecture to miss. All right, there are some bond energies. Those bond energies are not necessarily to be memorized. They are to be understood. You can see here that the bonds between X and X are much weaker than the bonds that you get. Between H and X, they're usually quite strong. Between C and X, they're quite strong. Between C and H, they're quite strong. This is the one you're trying to get rid of to go to more stable material. Starting with that, the initiation step should be logical by now. The weaker molecule breaks, and that gives you the radicals that you need to get started. So that's the basic stuff out of the way. There are some issues here, just FYI, that you might have to see in the future. You can do this with chlorine. You can do this with bromine. You cannot do this with iodine. The bonds just don't work up. It's actually endothermic. The whole process is endothermic. So it doesn't work for iodinations. It does work for fluorinations. It just works a bit too well. Okay? This is not something you'd want to do ever in your lives, right? That is so exothermic it blows up. So don't be blowing things up with the radical fluorinations. They just don't happen. Fluorine's kind of fun because it does all sorts of fun stuff like eats glass. You can't do fluorine reactions in regular glass because it eats the glass. Kind of a nasty little guy. All right, so let's take a check there. We will do chlorinations, we will do brominations, and that's where we go from now on. In terms of the bond energies, this is just finishing that off. There's the proof. The halogenation reaction for chlorine is quite exothermic. The halogenation for bromine is fairly exothermic. That will make a difference in a second. And it's all to do with what? Which do you think is more reactive, a chlorine radical or a bromine radical? Think about this. It's very similar to what we just talked about. Would you rather have a radical on a chlorine atom or on a bromine atom? Which one would you rather lose an electron? Bromine, right? Less electronegative, it's easier to handle that loss. So we'll see now that radicals have different reactivities. Bromine is actually less reactive than chlorine. Radical is impetuous, it just grabs, chlorine is impetuous, it grabs what it wants. Bromine chops around. So we'll see that in the next couple of slides. All right, here's where it gets heavy. It wasn't heavy already. On the left-hand side, the argument here is that the rate determining step for these processes is the abstraction of that hydrogen from carbon. It is the radical taking off a hydrogen from carbon to produce a carbon radical. And they are quite different. In this step, you can see now that the first process here, two different things. There's your CH4 molecule with your chlorine radical. Over here is your CH3 radical and your molecule of HCl. There are several comments to be made here. This is a low barrier. It's a fast reaction. On the other hand, it's an exothermic process. Write that down with your writing implement or your nose, wherever you use to write, just write it down. And on the right-hand side, it differs. This is something you really have to scratch your heads about. In the bromination step, it turns out that the activation barrier is quite high. So this is a slower reaction. But it's also endothermic. Eventually it's worth it because we get down here somewhere it's overall exothermic, but the first step here is slow. So when we look at this system, we've got to be very careful. There is a big difference between the graphs for a chlorination and a bromination. And that leads to, again, what we call selectivity. In this case, it would be regioselectivity based on where the reaction happens. So keep an eye. If you're looking at anything this weekend, there is a good slide to look at, deciding that one is going to be different to the other. That's a fact. Now we have to be careful. We're heading into this idea of isomers again, major versus minor. If you mix chlorine or bromine with alkanes, you get mixtures of products. We have to understand where they come from, which is major and why. This is nothing more complicated than what we've done, but obviously it's a different system because it now involves radicals, not carbocations. If you mix propane with halogens such as bromine or chlorine, you'll get a secondary product and a primary product. That's a fact. Why can I get two products? I have two types of hydrogen. Two hydrogens in the middle, other hydrogens at the end. Now think about this. I have two of the internal hydrogens. How many of the external hydrogens do I have? 6, right? 6 of these guys, 2 of these guys. You've really got to be on your toes here, and hopefully the point is you really have to have developed as a chemist. Which one do you get more of, left or right? You get more of this. This is the major product, okay? This is the major product. You get less of this. And you have to be careful how you say this. You're going to get more of the secondary than the primary. Why? Give me some ideas. Well, you've been reading, haven't you? You've been reading. You know what you're doing, right? This is very much like the processes we saw before. You get more of the secondary product because you get more of the secondary radical. Why is the secondary radical better than the primary radical? More stable. Because of what? Holderman's here today. Because of what? Which is? It certainly is, right? So secondary systems have more than primary systems, so therefore the secondary radical is better than the primary radical. That's all it is. But you've got to keep your radicals separate from your carbocations, right? You mix your radicals, your carbocations, it all goes wrong. So there's the argument. Statistically, you've only got 2 of those internal hydrogens, you've got 6 of these guys. But still, you get this as the major product. So it's all about the stability of the radical intermediate and the stability of the transition state getting to that intermediate. We have dealt with those ideas before with cations. Now you have to put it together with radicals. Not particularly easy. There's the fact. If you mix propane with chlorine molecules and you do the free radical halogenation by heating it or shining light on it, you get about 60% of this and you get about 40% of that. So it cannot just purely be statistical because you had more of the primary hydrogens and fewer of the secondary hydrogens. It has to do with the structure of the intermediate species. So let's argue this again. How much more stable do you think this molecule is versus this molecule? You have some carbon-chlorine bonds, you have some carbon-carbon bonds, you have some carbon-hydrogen bonds. Do you think there's a massive difference in their stability? No, there isn't. No, right? So that tells you that this reaction is not going to happen based on the thermodynamic outcome. It's not going to be based on relative stabilities of products. It's based on the intermediate stabilities. And that's something you must keep a track of. That graph now will explain this. In that previous example, we had a choice of making a primary radical, which we don't particularly like, or a secondary radical, which we prefer. Now, this isn't the whole reaction. This is the hydrogen abstraction step. This is the radical going after the molecule, the alkane molecule, and taking off that hydrogen. It gives you a molecule of HCl or HBr, and it gives you a carbon radical. So on the right-hand side, this is not the final product. This is the primary radical. This is the secondary radical. You go all the way back to chapters 5 and 6 when we started to actually introduce mechanism. We saw graphs like this. In this outcome, it's not necessarily down here. It's all about up here. Now think about this. We'll see some pictures in a minute when we draw some transition states. There they are. Up here and up here, you need to be aware of what's happening. You're breaking a carbon-hydrogen bond. Your X radical is coming in, getting hold of that hydrogen, and breaking it away from your carbon. Your carbon is becoming a radical. So where would you rather have that growing radical? On a secondary carbon or a primary carbon? Secondary, yes, because Hyperconjugation, blah, blah, blah. You can sit down now, thank you. You would rather have your radical growing on a secondary carbon than you would on a primary carbon because there's more help on that secondary carbon. So now it turns out that the transition state for the secondary process is lower than the transition state for the primary process. So which is faster? Let's go into the secondary radical. So it coincides with the fact that that actually is the more stable radical, but this is the more stable transition state and therefore the faster process because of the same ideas. You've got help in the transition state from the neighbors. More neighbors in the secondary system, fewer neighbors in the primary system. So now we can say that the secondary radical is formed through the lower energy pathway. In other words, in English, it's formed faster. That's all there is to it. You just have to get your heads around that. So now let's think about the next step. And again, it's Friday, I've got 7 minutes. Let's do this now. Let's repeat it on Monday after you've had a chance to digest it. Look at my numbers. On my previous slide, I had 60% of the chlorine. I had 40% 60% in the secondary position, 40% in the primary position. That's not much use to us. That's 3-2. That means separations. That means industrially, economically, not that great because you get a lot of waste. Well, go to this system. Look at that. Bromination, for some reason, gives me a much cleaner reaction in which you get 97% secondary and only 3% of the primary. That's a big difference. Well, it's still secondary versus primary. You've got to see the same graph. The secondary radical is formed faster. But now there's something else happening in terms of the overall process that changes this ratio of products. That's a very useful reaction. 97% means very little waste. Great. Well, it now turns out we've got to worry about the nature of the radical. In that previous slide, I had chlorine radical. In this slide, I've got Br radical. And the statement at the bottom basically says the Br radical is less stable. The Br radical is less reactive than the chlorine radical. Why is Br radical less reactive than chlorine radical? Why is chlorine radical less stable than Br radical? Say again? What does that mean in English? Electronegativity, right, electronegativity. The chlorine radical is upset because it lost an electron, it wants it back, damn it. So it goes after things and it starts to attack them in fast processes. Whereas the bromine radical's kind of, hey, I'm a bromine radical. I'm just going to kind of hang out until the best thing shows up. And that gives you the secondary outcome. You can't explain it like that in an exam, but that's kind of what's happening. So we get selectivity. And that selectivity now is really tricky. It's really difficult to get this into your head to understand it so you can answer problems. Well, we drew graphs a couple of slides ago, a while back. There we are, right there. The propagation step for chlorination, the first abstraction, is actually exothermic, and for bromination, it's endothermic. Jump ahead a few slides. They are the same graphs, just focusing on the one step. Don't forget what's happening here is your atom, your chlorine or your bromine, has found an alkane. Hello, alkane. And it's going to go for a primary carbon and its hydrogen or a secondary system. And the chlorination is super fast. You can see a fairly low reaction barrier right there. And the bromination step is slower. And what that leads to is selectivity. The chlorine radical just wants to get this thing over with. It wants an atom. It's not so concerned about whether it's taking a primary or secondary. But the bromine radical, hey, just hanging out. And it recognizes that taking a secondary system or taking a secondary hydrogen is more beneficial to the system overall. So the bromine radical shops around for the best deal. And it will take a secondary radical over a primary in the numbers that we just saw. So I'm going to finish with this slide. I've got 5 minutes. I'm going to do it now and come back to it on Monday. But we are talking about what's happening up here. First off, in this example, this is exothermic in that step. This is endothermic in that step. And we must go all the way back to the earlier chapters when we dealt with things like the Hammond postulate. What was that? Can we remember? What does the Hammond postulate tell you? It's Friday, it's payday. It's the weekend. Hammond was aware of those things, but that wasn't his postulate. Does anybody remember this? Go on. Absolutely, that's exactly what it is. Yeah, well done, very good. This guy up here, which we have to calculate and we can't see transition states through spectroscopy. We can't measure them directly. So the argument now is that if we want to have some idea of what this thing looks like, then we've got to worry about what's close by. What's a real species that we can see? So in this case, it's an early transition state where the transition state looks a lot like the reactants. On the right-hand side, it's a late transition state because it's getting closer to the products. And so the transition state over here looks more like the products of the step, which happen to be the radical intermediates. So on the left-hand side, this reaction is happening, and you really don't sense the nature of the radical as much as you do on the right, because the transition state looks more like the starter materials. You're developing some radical in that transition state on the carbon, but not to the extent you do in the bromine. And let's think about this as well. These things are going, your chlorine can attach or attack and it can back off. The bromine can attack and it can back off. You've got this sort of idea of going up and down these hills and trying to find maybe the best situation. So in this example, you have a very, very, very reactive chlorine that just wants to become neutral and stable. And it approaches our molecule, and there is a sense of secondary versus primary, but not a great deal because the chlorine is ruling the system. The chlorine wants a hydrogen, and it really doesn't care about which one it takes off. On the right-hand side, we have bromine. Bromine's so laid back, just wants the best for everybody. It's the hippie of radicals, right? So it goes after the molecule, and it says, dude, you're a primary system. That's not the best overall outcome. So it backs off, and it goes and says, oh, secondary. And it goes after the secondary system, and all of a sudden it's like, dude, we're getting a secondary radical. Product. That's how it works. So what you need to do for Monday is to look at these pictures and look at those diagrams so that we can get this finished. I'm not done yet. I've got 2 minutes. The argument at the end of all that is to do with shopping, basically. Right? I am a chlorine radical. My wife is a bromine radical. I go out shopping. I want to go home and watch the game. I know what I want. I go in the shop. I buy it. I'm done. I might not have got the best deal, but I got home and I got to watch the game. My wife is a bromine radical. This involves shopping at every possible conceivable place that you can possibly shop at to find one thing. But she gets the best deal, and that's it. Have a nice weekend. We'll see you on Monday.